Okay, picture the universe. This huge, vast space, billions of galaxies, countless stars. It's pretty amazing.
Absolutely mind-bending when you really think about it.
But here's the kicker. All that stuff we see, stars, gas, dust, planets, that's only, about 5% of everything?
That's right. Just a tiny fraction. The vast majority, around 27%, is something completely different, something invisible. Dark matter.
Invisible, yeah. Can't see it, can't touch it. But somehow, its gravity is running the show, holding galaxies together, shaping everything. It's a huge puzzle.
It really is. And that's what we're diving into today.
Exactly. For you listening, maybe you're fascinated by these big cosmic questions, but, want it spelled out clearly.
That's the goal. We want to unpack the evidence for dark matter, look at the main ideas about what it could be, and sort of figure out why this invisible stuff is so incredibly important.
We'll be drawing on some great materials here, the dark matter deep dive notes, and also getting some perspective from Richard Panek's book, The 4% Universe.
It provides a fantastic narrative context for all of this.
Definitely. So by the end, we hope you'll have a clearer picture on things like, what is dark matter, fundamentally?
And what's the actual proof? What makes scientists so sure it's there?
Yeah, and what are the candidates? What could it be made of? And, why should we even care about something we can't see?
Let's start right there. What is dark matter at its core?
Okay, so the basic idea is it's matter, but it doesn't interact with light, right?
Exactly. It doesn't interact with the electromagnetic spectrum. That means no emitting light, no absorbing it, no reflecting it, radio waves, visible light, X-rays, none of it. It's just dark.
Hence the name. Makes sense.
But it definitely has mass. And it occupies space, which fits NASA's definition of matter. We just can't see it directly. We only know it's there because we see its gravitational effects on the things we can see.
Like stars and galaxies moving in ways they shouldn't based on the visible stuff alone?
Precisely. And it's not a small amount either.
No kidding. What were those numbers again?
Okay, so of the total mass and energy in the universe, dark matter is about 27%. Ordinary matter, everything we know and see, is just under 5%.
Wow. What's the rest then?
The other, roughly 68%, is dark energy, which is a whole other mystery related to the universe's expansion. But if we just look at matter, dark matter makes up something like 85% of all matter.
85%? That's staggering. So most of the stuff out there is invisible to us.
It really flips your perspective.
Yeah.
It's not just floating around randomly. It plays a crucial role.
Like a cosmic scaffold or something?
That's a great analogy. It's thought to form this vast, interconnected web throughout the universe, a kind of gravitational scaffolding that attracts ordinary matter. It's the framework upon which galaxies form and cluster.
The cosmic glue holding things together.
Exactly. Without it, galaxies might just fly apart. And this connects directly to that missing mass problem, doesn't it?
Right, that was the original clue, wasn't it? Scientists looked at galaxies, calculated the mass needed to explain how they moved or held together.
Based on the gravity of the stars and gas they could see.
And the numbers just didn't add up. There was way more gravitational pull than the visible matter could account for.
Exactly. A huge discrepancy. That missing mass pointed directly toward something unseen, something massive, providing the extra gravity. That's dark matter.
So that unseen scaffolding you mentioned, the dark matter, provides the extra gravity needed to explain what we observe.
Yes, and it's crucial for understanding how structures formed in the first place. Simulations showed that without dark matter clumping first in the early universe, creating these gravitational wells, ordinary matter wouldn't have collapsed quickly enough to form the galaxies and clusters we see today.
So it's not just holding things together now, it was essential for building them in the first place.
Absolutely fundamental.
Okay, let's dig into that evidence. Mentioned galaxies moving weirdly. That brings us to galaxy rotation curves, right? Vera Rubin's work.
Yes. Absolutely pivotal work in the 1970s by Vera Rubin and her colleagues. Now think about our solar system. Planets closer to the sun orbit faster than planets farther out, like Mercury versus Neptune.
Makes sense. Gravity is stronger closer in. Kepler's laws. Right?
Exactly. So intuitively, you'd expect the same in galaxies. Stars farther from the center, where most of the visible mass seems concentrated, should orbit slower.
But that's not what Rubin found.
Not at all. She meticulously measured the speeds of stars way out in the spiral arms of galaxies and found they were moving just as fast, sometimes even faster than stars closer to the center. The rotation curves were flat instead of dropping off.
Flat, meaning constant speed way out. How's that possible?
The only way it makes sense is if there's a huge amount of unseen mass extending far, far beyond the visible edge of the galaxy, a massive halo of dark matter.
Ah, so this halo provides the extra gravity needed to keep those outer stars orbiting so fast.
Precisely. And this wasn't just one or two galaxies. It was a consistent pattern found in many spiral galaxies, including our own Milky Way. In some cases, this dark matter halo might contain up to 95% of the galaxy's total mass.
95%, wow. So Vera Rubin's work really cemented the idea.
It absolutely did. Fritz Zwicky had noticed something similar in galaxy clusters way back in the 30s, this missing mass idea. But Rubin's systematic study of individual galaxies showed this wasn't just a cluster thing, it was fundamental to galaxies themselves. It moved dark matter from a curiosity to a central problem in cosmology.
So the visible galaxy is just the tip of the iceberg, sitting in this enormous invisible halo.
That's the picture, yes. The stuff we see doesn't have nearly enough gravity to explain the speeds. Something else, something dark, has to be there.
Okay, so spinning galaxies give us one big clue. What about gravitational lensing? That sounds like something out of Einstein.
It is. It comes directly from Einstein's theory of general relativity. Massive objects warp space-time around them. And light, as it travels through space, follows these curves.
So heavy things bend light beams.
Exactly. And really massive things, like entire clusters of galaxies, can act like giant cosmic lenses. They bend and magnify the light from even more distant galaxies sitting behind them, from our perspective.
Like looking through the bottom of a wine glass, distorting the view.
Kind of, yeah. And the amount of bending, the amount of distortion, tells you the total mass of the lensing object, the galaxy cluster in this case.
Total mass, meaning visible stuff plus dark matter.
That's the key. When astronomers measure the lensing effect around clusters, they consistently find that the mass required to produce the observed bending is far greater than the mass of all the stars, gas, and dust they can see in the cluster.
So again, there's way more gravity, way more mass than meets the eye.
Precisely. And there's also weak gravitational lensing. It's a more subtle effect, looking at tiny, tiny distortions in the shapes of thousands or millions of background galaxies across a large patch of sky. By analyzing these subtle alignments, we can actually map out the distribution of mass, including dark matter, over huge cosmic distances.
Mapping the invisible. That's incredible. You mentioned the bullet cluster before. How does that fit in?
Ah, the bullet cluster. It's often called the smoking gun evidence for dark matter. It's actually two galaxy clusters that have collided, or rather passed through each other.
A cosmic collision. What happened?
Well, most of the ordinary matter in galaxy clusters is actually super hot gas floating between the galaxies. When the clusters collided, this gas from each cluster slammed into the other, interacted electromagnetically, and slowed down, kind of like a traffic jam. You can see this hot gas using X-ray telescopes.
Okay, so the ordinary matter interacted and got stuck in the middle, relatively speaking.
Exactly. But when astronomers mapped the total mass distribution using gravitational lensing mapping where the gravity is strongest, they found something different.
What did they find?
They found that most of the mass, the source of the strong lensing, wasn't where the hot gas was. It was located in two clumps that seemed to have passed right through the collision, almost unaffected, ahead of the slowed down gas.
So the gravity, the mass kept going while the visible stuff got slowed down.
That's exactly it. The dark matter, interacting primarily through gravity and very weakly otherwise, just sailed through the collision. The ordinary matter, the gas, didn't. This physical separation between the bulk of the mass, seen via lensing, often shown in blue in images, and the bulk of the ordinary baryonic matter, the X-ray gas, often shown in pink, is incredibly strong evidence.
Wow, you can literally see the dark matter pulling away from the ordinary matter after the crash.
It's about as close to a direct observation as we can get. It strongly suggests most of the mass is non-luminous and doesn't interact strongly with itself or ordinary matter, which is exactly what we expect from dark matter. It's very hard to explain the bullet cluster just by modifying gravity.
That does sound pretty conclusive. Okay, one more big piece of evidence. The cosmic microwave background and large-scale structure. How does the universe's earliest light tell us about dark matter?
The CMB, the cosmic microwave background, is like the universe's baby picture. It's the leftover heat from the Big Bang, released when the universe was just about 380,000 years old.
And it's not perfectly smooth, right? There are tiny temperature differences.
Exactly. Tiny fluctuations and isotropies. We're talking differences of like parts per 100,000. But these tiny temperature variations correspond to tiny differences in the density of matter in the very early universe.
Little seeds of structure.
Precisely. And the exact pattern of these hot and cold spots, their size and distribution across the sky, is incredibly sensitive to what the universe was made of back then.
So analyzing that pattern tells us the ingredients.
Yes. When scientists analyze the CMB power spectrum, basically, how strong the fluctuations are at different angular scales, the data overwhelmingly points to a universe where about 85% of the matter content in that early era was non-baryonic dark matter.
Non-baryonic meaning? Not protons and neutrons, not normal stuff.
Correct. Not the stuff that makes up you, me, stars, and planets. Furthermore, dark matter was crucial for growing those tiny initial fluctuations into the structures we see today.
How so?
Well, in the early universe, ordinary matter was coupled to radiation, and the pressure from that radiation resisted gravitational collapse. Ordinary matter couldn't easily clump together.
But dark matter doesn't care about radiation pressure.
Exactly. It doesn't interact electromagnetically. So dark matter could start collapsing under its own gravity much earlier, forming these gravitational potential wells.
Like gathering spots.
Right. Then, once the universe cooled enough for ordinary matter to decouple from radiation, it could fall into these pre-existing dark matter wells, accelerating the formation of the first stars, galaxies, and eventually the cosmic web.
So without dark matter jump-starting the process, we wouldn't have formed structures as quickly or as extensively as we see them.
That's what the models strongly indicate. Ordinary matter alone wouldn't have had enough gravitational oomph against radiation pressure. The CMB analysis also helps confirm the universe is geometrically flat and nails down those proportions. 5% ordinary matter, 27% dark matter, 68% dark energy.
And haven't they even mapped dark matter using the CMB itself recently?
Yes, through CMB lensing. Just like galaxy clusters lens background galaxies, the large-scale distribution of dark matter between us and the CMB surface slightly lenses the CMB light itself. By studying these subtle distortions, experiments like the Atacama Cosmology Telescope have created maps showing the clumpy distribution of dark matter, and it matches beautifully with what our cosmological models predict.
It's just evidence piling up from every direction, every scale. So, okay, we're pretty convinced it's there. What could it be? What are the candidates?
The million-dollar question, or maybe trillion-dollar question. We know what it does gravitationally, but we don't know what it is fundamentally. That's one of the biggest mysteries in physics. But there are some leading ideas.
Let's hear the lineup of suspects. WIMPs seem to be a big one.
WIMPs, weakly interacting massive particles, were the front runners for a long time and still a strong possibility. These are hypothetical particles, likely much heavier than protons.
Okay, massive and weakly interacting.
Meaning they interact, we think, through gravity and the weak nuclear force. The force involved in some radioactive decays, but not electromagnetism or the strong nuclear force. So they wouldn't interact with light, and they wouldn't interact much with ordinary matter either.
Makes them hard to detect.
Extremely hard. They're predicted by theories that go beyond our current standard model of particle physics, like supersymmetry. Because they're massive, they'd be slow-moving, which fits the idea of cold dark matter needed for structure formation.
Cold meaning slow, not temperature-wise.
Right. Cosmologically cold means slow-moving relative to the speed of light in the early universe.
So how are people trying to find these WIMPs?
3 main ways. Direct detection. Building huge, ultra-sensitive detectors deep underground, shielded from other radiation, hoping to catch the rare ping of a WIMP bumping into an atomic nucleus inside the detector. Experiments like Xenon 1T, LUX Zeppelin are examples.
Okay, wait for a direct hit. What else?
Indirect detection. Looking for the byproducts of WIMPs annihilating each other. If 2 WIMPs meet, especially where dark matter is dense like the galactic center, they could annihilate and produce detectable particles like gamma rays or neutrinos. Telescopes search for these signals.
Looking for the debris. And the third way?
Collider searches. Trying to create WIMPs in high-energy collisions like at the Large Hadron Collider, LHC. If WIMPs are produced, they'd zip out of the detector without interacting, carrying away energy and momentum. Physicists look for this missing energy signature.
Trying to make them from scratch, I heard something about a WIMP miracle.
Ah, yes, the WIMP miracle. It's a fascinating theoretical coincidence. If you assume a new particle exists with roughly the mass and interaction strength expected for a WIMP from theories like supersymmetry, and you calculate how many will be left over from the Big Bang,
Yeah.
you naturally get an abundance that's remarkably close to the amount of dark matter we actually observe today. It seemed too good to be just a coincidence.
That sounds compelling. But have we found them?
That's the problem. Decades of searching, with incredibly sensitive experiments, and still no definitive, undisputed detection. The null results have ruled out many of the simplest WIMP models, or put very tight constraints on their properties. That Xenon 1T anomaly a while back turned out to likely be background noise.
So the miracle hasn't quite panned out yet. What's next on the list? Axions.
Axions are another very popular candidate, quite different from WIMPs. They are predicted to be extremely lightweight particles, potentially billions or trillions of times lighter than an electron.
Whoa, tiny, but still dark matter.
Potentially, yes. They're also expected to interact very weakly. Interestingly, axions weren't invented for dark matter. They were proposed back in the 70s to solve a completely different problem in particle physics called the strong CP problem. But it turns out, if they exist and were produced in the right amounts in the early universe, they could be the dark matter.
A 2-for-1 deal in physics. How would we detect something so light and weakly interacting?
The main idea relies on a predicted property. In the presence of a strong magnetic field, an axion could convert into a photon, a particle of light, typically in the microwave range.
So you use a big magnet and look for faint microwave signals.
Essentially, yes. Experiments like ADMX, Axion Dark Matter Experiment, use powerful magnets and sensitive microwave receivers to basically listen for the hum of axions converting into photons from our galaxy's dark matter halo. They're a very compelling alternative, especially as WIMP searches have come up empty so far.
Okay, heavy WIMPs, light axions. What else? Sterile neutrinos.
Sterile neutrinos are another possibility. We know about 3 types of active neutrinos, electron, muon, tau, which interact via the weak force. Sterile neutrinos are hypothetical cousins that wouldn't even interact weakly, only through gravity.
Even more elusive.
Potentially. They're theorized to be heavier than the active neutrinos, maybe in a range that can make them warm, dark matter moving a bit faster than cold dark matter in the early universe. Their existence could also help explain why the active neutrinos have mass, which isn't explained by the standard model, and maybe even the universe's matter-antimatter asymmetry.
How do you search for those?
One potential signature is looking for faint X-ray signals. If sterile neutrinos exist and occasionally decay, they might produce an X-ray photon with a specific energy. There have been some tentative hints, but nothing conclusive yet. And just to be clear, the regular active neutrinos are too light, too hot to be the bulk of dark matter.
Right. Okay, one last category you mentioned earlier. Machos. Massive astrophysical compact halo objects. Sounds like normal stuff, just hidden.
Exactly. Machos are things made of ordinary baryonic matter, but they're faint or invisible. Think black holes, neutron stars, maybe brown dwarfs, failed stars, or dim white dwarfs floating around in the galactic halo.
Could enough of those account for the missing mass? How did they look for them?
The primary technique was microlensing. If a macho passes directly between us and a background star, its gravity briefly magnifies the star's light. So you monitor millions of stars and look for these temporary brightening events.
Did they find many?
They did find some events, confirming these objects exist. However, long-term surveys concluded that machos could only account for a small fraction, maybe 20% at most, of the galaxy's halo mass needed to explain rotation curves. Recent studies looking specifically for primordial black holes formed in the very early universe, have constrained them even further, suggesting they make up only a few percent, if any, of the dark matter.
So machos are probably not the main answer.
That's the general consensus now. While they exist, they don't seem numerous enough. The evidence still points strongly toward some kind of new non-baryonic particle being the dominant form of dark matter.
It's quite a range of possibilities. But what if What if we don't need new particles? What if the problem isn't missing matter, but our understanding of gravity? What about those alternative theories?
That's a perfectly valid scientific question to ask, and there are researchers exploring this. The most prominent alternative is MOND, modified Newtonian dynamics.
MOND, what's the idea there?
Proposed by Mordechai Milgram in the 80s, MOND suggests that maybe Newton's law of gravity isn't quite right under conditions of very, very low acceleration, like those experienced by stars in the outer parts of galaxies.
So gravity behaves differently when it's weak.
Essentially, yes.
Yeah.
MOND proposes that below a certain tiny acceleration threshold, gravity becomes slightly stronger than Newton would predict based on the visible mass alone.
And could that explain the flat rotation curves without dark matter?
Remarkably, yes. MOND is quite successful at predicting galaxy rotation curves using only the mass of the stars and gas we can see. It also naturally explains an observed relationship called the baryonic Tully-Fisher relation, which connects a galaxy's luminosity to its rotation speed.
That sounds pretty good. Why isn't MOND the standard theory then?
The main issue is scale. While MOND works well for individual galaxies, it struggles significantly when you try to apply it to larger structures, like clusters of galaxies. It generally can't explain the observed dynamics or gravitational lensing in clusters without invoking some unseen mass anyway, often similar in amount to the dark matter required in standard cosmology.
And the bullet cluster.
The bullet cluster is a huge problem for MOND. That clear separation between the mass, seen by lensing, and the ordinary matter, the gas, is very difficult, if not impossible, for MOND to explain without adding some kind of dark collisionless component back into the picture.
So it sort of defeats the purpose.
In many ways, yes. Also, the original MOND was non-relativistic, not compatible with Einstein's theories. Relativistic versions like T's have been developed, but they've run into their own problems fitting observations like the CMB details and, more recently, the speed of gravitational waves, which seems to match the speed of light very closely, something many modified gravity theories struggle with.
So while intriguing, MOND hasn't been able to replace dark matter as the comprehensive explanation.
That's the current situation. The dark matter paradigm, despite the mystery of the particle's identity, provides a much more consistent framework for explaining observations across all cosmic scales, from galaxies to clusters to the CMB and the formation of large-scale structure. Most cosmologists favor it for that reason.
Okay, so assuming dark matter is real, and it's the dominant form of matter, why is it so significant? Why does it matter so much?
Oh, it's absolutely crucial. Its biggest impact is on galaxy formation and stability. As we touched on with the CMB, those early dark matter clumps acted as the gravitational seeds.
The wells that ordinary matter fell into.
Exactly. Without those dark matter halos forming first, the gravity from ordinary matter alone likely wouldn't have been strong enough to overcome cosmic expansion and gas pressure to form galaxies as large or as early as we see them.
So our own Milky Way might not exist without it.
It would certainly look very different if it existed at all in its current form. And the dark matter halo is also thought to be vital for the stability of existing galaxies, provided the gravity needed to hold on to those fast-moving outer stars over billions of years.
Keeping them from flying off into space.
Right. And on even larger scales, dark matter dictates the structure of the cosmic web, that network of filaments and voids.
The scaffolding idea again?
Yes. Gravity pulls matter together, and since dark matter is most of the matter, its distribution governs where galaxies form and cluster, creating those long filaments separated by vast empty regions, the voids. Understanding dark matter is key to understanding the entire architecture of the universe.
So,
It would require a complete rewrite of cosmology. Our understanding of structure formation, galaxy evolution, the expansion history of the universe, all of it relies heavily on the presence and behavior of dark matter.
it really puts things in perspective, which brings us back to Richard Panek's book, The 4% Universe. It sounds like he captures this bigger picture really well.
He absolutely does. It's a fantastic book because it tells the story of how scientists realize that ordinary matter, the 4% or 5%, is just a cosmic afterthought in a way.
The story behind discovering the 95% we can't see.
Exactly. He covers the intertwined discoveries of both dark matter and dark energy, highlighting the key experiments and the people involved, like Vera Rubin, of course. He talks about the challenges, the aha moments, even the rivalries in human side of the science.
Making complex cosmology accessible through narrative.
Yes, he's a great storyteller.
Yeah.
It gives you a real appreciation for the journey of discovery that led us to this picture of the universe dominated by mysterious dark components. It's not just about the physics, it's about how we figured it out.
Sounds like a great read for anyone wanting to dive deeper after this. We'll make sure there's info in the description.
Definitely recommend it.
Okay, so let's try and wrap this up. Key takeaways. Dark matter is invisible stuff. Makes up most of the matter in the universe.
About 85% of all matter, yeah. Its existence is inferred purely from its gravity.
And the evidence is strong, coming from multiple angles. Galaxies spinning too fast.
Flat rotation curves, thanks in large part to Vera Rubin.
Light bending around massive objects more than it should.
Gravitational lensing, both strong and weak, with the bullet cluster as a killer example.
And the pattern in the universe's baby picture, the CMB, plus how structures formed.
All pointing consistently towards this massive, unseen component.
But we still don't know what it is.
That's the big cliffhanger. WIMPs, axions, sterile neutrinos. These are the main suspects, but the search continues intensely. It's one of the absolute biggest unsolved problems in all of science.
It really makes you wonder, doesn't it? How much more is out there that we're completely unaware of? What if our whole picture of reality is still just scratching the surface?
It's humbling. Discovering the true nature of dark matter, or perhaps finding we need an entirely new framework, could revolutionize physics and our place in the cosmos.
It's a reminder that the universe is probably stranger and more wonderful than we can currently imagine.
Absolutely. And it's an exciting time to be following the research. For anyone listening who wants to keep exploring, definitely look into the experiments we mentioned or check out more resources on cosmology.
And maybe pick up Richard Panek's The 4% Universe to get that broader story we talked about. Thanks for walking us through this cosmic mystery.
My pleasure. It's a fascinating subject.